Hello! In this video, we are going to prove the following theorem. Suppose R is a partial order on A. Then, every non-empty finite subset of A has a minimal element. Now, let's remind ourselves what a minimal element is. Well, we have a partial order R on A, and if we're also given B is a subset of A and M is an element of B, then, to say that M is a minimal element of B means the following. It means for all elements X and B, if X are M, then X is equal to M. Another way of putting this is there is not an element X in B such that X are M and X is not equal to M. Right? Both of these things mean that M is a minimal element of B. Okay, so now let's get into proving this theorem. Now the whole goal is to prove that every non-empty finite subset of A has a minimal element. So we're trying to prove a statement about every subset of A with some positive integer number of elements. So we're going to use induction. And the way we're going to use induction is we are going to show for all positive integers n, every subset of A with n elements has a minimal element. If we can prove this, then that will amount to proving this statement. So let's start with the base case. In the base case, we're trying to prove that this is true in the case where n is equal to 1. So really, we're trying to show that every subset of A with one element has a minimal element. Well, since we're trying to prove a statement about every subset of A with one element, give me an arbitrary subset of A with one element. I'll call it B. The whole goal is to show that B has a minimal element. Now, since B has only one element, let's call that element B naught. Now we want to show that B has a minimal element. Well, since B naught is the only element of B, it makes sense to show that B naught is a minimal element of B. And to show that B naught is a minimal element of B, what does that mean? Well, by our definition, it means we replace M with B naught. So really, we want to show for all X and B, if X are B naught, then X is equal to B naught. Well, since we're trying to prove a statement about all elements X and B, give me an arbitrary element X and B. Well, since B naught is the only element in B, X must be equal to B naught. And since X is equal to B naught, of course, if X are B naught, then X is equal to B naught. And the reason why we know this conditional is true is because the consequent is true. So, putting this together, we see that under the assumption X is any element in B, it follows that if X are B naught, then X is equal to B naught. So we've proven precisely this, which amounts to showing that B naught is a minimal element of B. So this completes the base case. Now let's move on to the induction step. In the induction step, we give ourselves an arbitrary positive integer where this is true. So let n be any positive integer and assume that every subset of A with n elements has a minimal element. The whole goal of the induction step is to show that this is also true for n plus 1. That is, we want to show that every subset of A with n plus 1 elements has a minimal element. Well, since we're trying to prove a statement about every subset of A with n plus 1 elements, let's give ourselves an arbitrary subset of A with n plus 1 elements. I'll call that set B. And from here, we want to show that B has a minimal element. If we can do that, then that will complete the induction step. So, to start, since B has n plus 1 elements, we know that B has at least one element in it. So let's just pick some element, I'll call it P. And let's consider the set B with the element P removed. Now, since this set is just the set B with an element removed, this set must have n elements. And I'm going to call this set B prime. But also note, B prime is a subset of B, and B is a subset of A. Therefore, B prime is a subset of A. So B prime is a subset of A with n elements. Well, we know that the induction hypothesis is true for every subset of A with n elements, so it must be true for B prime. Therefore, B prime must have a minimal element. Now let's just move back up to the top. Since B prime has a minimal element, we'll call that minimal element Q. It's going to be important to keep in mind that B prime is equal to B set minus P. And also, what does it mean for Q to be a minimal element of B prime? It means that for all x in B prime, if x are Q, then x is equal to Q. Remember, the whole goal is to show that B has a minimal element. If we can show that, that will complete the induction step. And to show that B has a minimal element, we're going to consider two cases, either PRQ or not PRQ. And in each case, we're going to show that B has a minimal element. Let's start with case 1, where PRQ holds. Now, in this case, we claim that P is a minimal element of B. And to see why that is, let's assume for a contradiction that P is not a minimal element of B. What does it mean for P to not be a minimal element of B? Well, it means that this is instead false. So instead of saying there doesn't exist an x in B such that x are P and x is not equal to P, we instead have that there does exist an x in B such that x are P and x is not equal to P. Now, since R is a partial order, we know that R is transitive. So, since X are P and P are Q, we have X are Q. Also, since X is an element of B, but not equal to P, this tells us that X is an element of B set minus P. So, X is an element of B prime. And now, let's use the fact that Q is a minimal element of B prime. That means we know that this is true, right? And this statement works for every element in B prime. So it must work for the x we have in our proof. So, taking the x to be the x we have here, we have if this is true, then this is true. Well, we know that this is true. That is what we have here. So we must have that this is true. So x is equal to q. Now, since x is equal to q and x are p, we can replace the x here with q. So we have qrp. But let's also remember that prq is true. So prq and qrp are true. And since R is a partial order we know that R is anti-symmetric, right? And since R is anti-symmetric, these two facts tell us we must have that P is equal to Q. And Q is equal to X, but X is not equal to P. So this tells us that P is not equal to P, which is absurd. So our assumption that P is not a minimal element of B leads to a contradiction. So we must instead have that P is a minimal element of B. So we've shown in the case where PRQ holds that B has a minimal element. So now let's move on to the case where not PRQ holds. And again, we want to show that B has a minimal element. Now in this case, we claim that Q is a minimal element of B. And to prove this, we want to show that for all x in B, if x are Q, then x is equal to Q. So let's give ourselves an arbitrary element x in B and assume that x are Q holds. From here, we want to show that x is equal to Q. Now to start, since not PRQ holds, we cannot have that x is equal to P. Because if instead x was equal to P, then we could replace the x with P, and we would have PRQ and not PRQ, which gives us a contradiction. So x is not equal to P. And so, since x is an element of B, but not equal to P, this tells us that x is an element of B set minus P, and therefore x is an element of B prime. And now, we can use the fact that Q is a minimal element of B prime, which means we know that this statement is true. And this statement works for every element in B prime, so it must work, in particular, for x. So taking x to be the x we have in our proof, it follows that if this is true, then this is true. Well, we know that this is true. That's what we have here. Therefore, this must be true. So x must be equal to Q. So what we see here is, given any element x in B, we have that if x are Q, then x is equal to Q. And that is precisely what it means for Q to be a minimal element of B. So we have shown that Q is a minimal element of B, as we claimed. So now, we see in either case, B has a minimal element. And so, that proves that B has a minimal element. And that was the whole goal of the induction step. And since we've completed both the base case and the induction step, this closes the induction. And the statement we are trying to prove regarding the induction amounts to proving that this statement is true. And so, we've proven exactly what we wanted to prove. So this completes the proof. And so yeah, that's pretty much it for this video.